When water is injected deep underground, it causes expansion in the surrounding formations. According to hydrologist Jeep Giambula from the University of Padua, this process could not only halt the gradual sinking of Venice, but may even raise parts of the city that have already subsided. However, it's important to note that land subsidence isn't always reversible. Once underground layers are compacted, much of the lost space is gone for good. Still, regaining even a portion of that ground is better than nothing. Beyond the potential to stabilize the land, injecting water underground offers Venice an innovative defense against worsening floods. The plan is ambitious. Surround Venice with 12 wells placed in a 6-mile wide ring. Over the course of 10 years, these wells will inject around 39 billion gallons of water into the subsurface. But this isn't just about pumping water randomly. Scientists have used a blend of old and new data to identify the best injection sites. Back in the 1980s, oil and gas companies used controlled explosives to perform geological surveys under the Venetian Lagoon. This data, combined with modern techniques, created a detailed 3D map of the underground layers, especially the impermeable clay beneath the city. This clay layer is key. Seawater will be pumped into sandy layers beneath it, ranging from 2,130 to 3,280 feet deep. The clay acts as a seal, preventing water from rising uncontrollably and ensuring it spreads horizontally instead. This setup lets scientists precisely control where and how much the ground rises. By carefully adjusting the water flow at each well, engineers aim to lift the entire city evenly. If one part of Venice rises faster than another, the uneven shift could damage buildings. Fortunately, models predict that any difference in ground elevation between 2 points, just 330 feet apart, will be less than 0.4 inches, small enough to go unnoticed. But water injection isn't Venice's only strategy. For centuries, Venetians have lived with regular floods. They're so used to it that, during the high water season known as acqua alta, many residents simply move their belongings upstairs to protect them. But something changed in 2020. On October 3rd, for the first time in decades, Venetians didn't need to move their furniture. That was the day the MOSE system was tested for the first time. MOSE is a network of 78 mobile gates installed at the 3 inlets where the Adriatic Sea meets the Venetian Lagoon. Each gate is about 66 feet wide. During calm weather, these gates remain underwater, completely invisible. But when tides threaten to rise above 43 inches, they swing up to form a barrier, shielding the city from floodwaters. The full system is expected to be operational by the end of 2025. It sounds like a perfect solution, but there are concerns. If the gates are closed too often, wastewater from the city could get trapped in the lagoon, leading to foul smells and ecological damage. It could disrupt the fragile marine ecosystem that supports the region's biodiversity. In short, while MOSE may protect Venice from flooding, it could also create new problems. This is where the water injection plan could make a huge difference. If Venice is physically elevated, the city will be naturally protected from rising seas, reducing the need to activate the MOSE gates so frequently. Scientists estimate that if sea levels in the region rise by 11 inches by the year 2100, the MOSE system would need to be activated about 35 times a year. But if the city is lifted through underground water injection, that number could drop to just 4 times a year. That's a dramatic difference. This approach could save the surrounding ecosystem from becoming a stagnant sewage lake. And there's another benefit: cost. The MOSE system has already cost around $6 billion, and that doesn't include future operational and maintenance expenses. In contrast, early estimates for the water injection project suggest a cost of just $255 to $383 million. It's far more affordable, though unfortunately, much of the funding for MOSE has already been spent and can't be recovered. Interestingly, the idea of using underground injections to manipulate land isn't new, and it has worked before. A 2010 study highlighted how fluid injection by oil companies caused ground uplift in parts of California, Canada, and elsewhere. In fact, water, gas, and even steam are regularly pumped underground for a variety of reasons: to increase oil production, store natural gas, replenish depleted aquifers, and more recently, to fight land subsidence caused by human activity. In some places, the injected fluids have lifted the ground by several inches, sometimes over months, sometimes over years. The technology has evolved over more than half a century. However, in most cases, these injections occurred in remote or sparsely populated areas, not in a historic, densely populated city like Venice. Still, the results are promising. Take Long Beach, California, for example. Decades of oil extraction there caused the ground to sink by nearly 29 feet. In 1958, a program was launched to reverse the damage by injecting fluids into the earth. The subsidence stopped, and in some areas, the ground even rose by up to 12 inches. In California's Central Valley, however, land continues to sink by as much as 8 inches per year due to excessive groundwater pumping and long periods of drought. Scientists have now created detailed maps of subsidence across the state, showing how urban areas and farmland alike are at risk. The causes are familiar: soil compaction, erosion, and water mismanagement. Canada has also made important contributions to this field. In Alberta's North Cold Lake oil sands, oil is extracted using a method known as cyclic steam stimulation. Steam is injected into deep underground layers, heating the bitumen until it becomes fluid enough to pump to the surface. Interestingly, at the injection sites, workers have noticed consistent ground uplift, around 12 inches, caused by pressure in the dense sand layers. These sands share characteristics with the terrain beneath Venice, offering valuable insights for Italian engineers. By studying what worked in Canada, scientists could more accurately predict how Venice's ground will respond and ensure it rises gradually and safely. Still, Venice's fight isn't only against water, it's also against energy policies that could backfire. One reason the city started sinking in the first place was unchecked gas extraction from underground reserves. As natural gas was pulled from the ground, the earth above it compacted and sank. In recent years, however, Italy's government considered returning to gas extraction, this time from the Po River Delta. Drilling in this area could be catastrophic. The delta is already vulnerable to intrusion from the Adriatic Sea. Any disruption could lead to flooding across 193 square miles of wetlands, located just an hour south of Venice. Fortunately, environmental groups stepped in and won a legal battle to halt the project. It's a huge victory for conservation efforts. Why? Because this delta isn't just a patch of marshland, it's a UNESCO-listed biosphere reserve. Over 350 species of birds live there, including herons and flamingos. The landscape is stunning, with ancient forests, sweeping sand dunes, and botanical gardens full of seaside pines. Gas drilling would have put all of this at risk. And for what? At most, the project could have extracted 353 billion cubic feet of gas, a short-term gain with potentially devastating consequences. In the end, Venice may be the world's most famous example of a sinking city, but it's far from alone. Many coastal regions are facing similar threats. What makes Venice unique is its combination of history, beauty, and bold experimentation. By blending old science with new solutions, like water injection and MOSE, Venice offers a rare glimpse into how we might preserve vulnerable cities around the world. The key lesson: with enough vision, it's possible not just to fight nature, but to work with it.